In this video lecture, we'll talk about extended real numbers. From there, go to the theory of how we sum a collection of numbers, and this will give us some remarks on integration theory. The video lecture is split into 4 parts. In the first part, we'll define the extended real numbers and the operations that we'll do in them. In the second part, we'll talk about the devil. In the third part, we'll talk about how to sum an infinite collection of numbers. And in the last part, we see already from what is hinted in the third part, what are the two overlapping integration theories that are considered. So we start with extended real numbers, and the set of extended real numbers, it is denoted either by R with a bar on the top of it, or by this closed interval that starts on minus infinity and ends at plus infinity. And it is just a set of real numbers to which we add two symbols, minus infinity and plus infinity. And we define operations on these elements, and of course all the operations have been defined already for numbers which are finite, which means numbers in this set, and we just extend them to include minus infinity and plus infinity in a way that keeps the algebra rules working as much as possible. So first we declare that minus infinity is smaller than any real number and also smaller than plus infinity. We also declare that adding any finite number to plus infinity gives plus infinity, and multiplying non-zero numbers by plus or minus infinity will give us plus or minus infinity in the only sensible way. The absolute value of minus infinity is plus infinity. If we multiply infinity, then we get always plus or minus infinity, depending on the plus and minuses that we have. Now, a property of these previous operations that have been defined so far is if two numbers can be compared, one number is less than or equal to the other, and by number I mean extended number, I'm allowing minus infinity and plus infinity. Then, if we add a third element of the set of extended real numbers to both of them, then they're still comparable in the sense that one of them is still to the left of the other one or less than or equal to the other one, as long as this sum here is finite. Sums are not always defined in the set. There's one case when it's not defined, and it will get a section that we'll discuss it later on. Defining these operations this way will be really very convenient. And here's already some hint of how convenient it can be. We want to compute the limit of the sum of two sequences. We know this is the limit of the first sequence plus the limit of the second sequence if both have a limit. Well, they do have a limit. The first one has a limit equal to 2, the second one has a limit equal plus infinity. We know how to add 2 and plus infinity on this space. This is just infinity. So you should see the references mentioned in the lecture notes for the complete definitions. It's very long and tedious, and it's not included neither in this video lecture nor in the lecture notes with all the details. Now this is the perhaps most controversial part, which nevertheless is a consensus when we do measure theory, which is we define 0 times infinity to be 0. This is very convenient. It really simplifies the expositions. It saves us the trouble of considering specific cases whenever some set has measure 0, but things on that set take value infinity, and so on. So even though in many branches of mathematics 0 times infinity should be left undefined and be considered as an indeterminate form or anything like that, in measure theory it is 0, and that's because basically the area of this rectangle with infinite height and 0 width, the area of this rectangle is 0. Or because the integral, if we integrate a function that is only takes positive values in a few points and eventually takes value infinite in some point, but except for those points is 0 everywhere else, we want to say the integral of that function is also 0. So this is why we define, just for convenience, 0 times infinity to be 0. There are a few caveats to consider in this operation, which is cancellations no longer work. At least not all of them, and we should be careful before we do cancellations. Well, for instance, if we know that adding A to numbers B and C, we get the same result, that doesn't mean B equals to C. Or if A is strictly less than B, and we add a number or we add an element of this space to both A and B, it doesn't mean they are strictly less than. This one, the first one would be strictly less than the second one as it used to be. And that's the counterexample here would basically be 5 plus infinity is not less than 7 plus infinity. This is not true. Another property that we'll break down is the property that the limit of the product is always the product of the limits. And here's a counterexample. If we take the two sequences to be n and 1 over n, so the limit of the first sequence is infinite, the limit of the second sequence is 0, so the product of these two limits is 0. And on the other hand, here the limit of the product of these sequences is 1, and they are different. Finally, not every operation can be defined in this space of extended real numbers, in the sense that if we try to define it, it would break down many of rules of algebra that are so convenient to use, so we leave them undefined. First is we cannot divide by plus or minus infinity. If we divide the finite number by plus or minus infinity, yes, that would be 0, but we'll never need it, and so let's not do it, because then we don't need to check if the number in the numerator is finite. Second, and this is the problematic one, if we try to compute the difference between plus infinity and plus infinity, or if we try to add plus infinity and minus infinity, we cannot define that. This will cause a lot of headache, and this is the topic of the next section of this video. So continuing from the previous section, here we say what is the most problematic case in this theory, in measure and in integration theory. And the problem is exactly when we get plus infinity and minus infinity being added together, or some plus infinity on one side of the equation and plus infinity on the other side of the equation, and we try to figure out what that means. This is really something that measure theory does not handle very well, and we'll do everything we can do to avoid this. So most of the theory is just trying to prevent this from happening. If this happens, it's game over. We cannot compute this difference, so we cannot compute the difference between two functions if some of them takes value plus infinity and the other one takes value minus infinity on the same point, and so on. So there's not so much to say about this right now. It's just to keep in mind that this plus infinity and minus infinity really is the bad element in this theory, really is the villain in the theory. Well, actually, yes. When I say there is not much to say about it right now, we'll see that right in the next second part of this video, we'll see that yes, this plus infinity minus infinity will cause trouble already in the simplest of the contexts.